right, should we get this party started? I think we are ready. We're in the right place if you're here to learn about astronomy and a little bit of geology at the same time. I'm Jason. I'm the lecture coordinator here. Welcome to San Francisco Amateur Astronomers. Glad you could make it. Really appreciate the support. We had a fantastic dinner beforehand talking with Professor Schaefer about everything from hobbies to planets to astronomy. It was a fantastic time. She's in her spare time is an avid rock climber, a PhD in astronomy, or from?
It was in astronomy.
It was astronomy. Thank you. From Harvard. I myself have only heard a little bit of her speak, and I'm really looking forward to learning more. I, for one, it's easy to take it for granted that we live on a planet with water, with this much. Really curious to learn where it all came from. So, without further ado, I'll hand it over to Professor Schaefer. Thank you.
Thank you, Jason, for the invitation to come talk to you. My name's Laura Schaefer. I'm an assistant professor at Stanford University. I am in the Earth and Planetary Science department there. Jason mentioned my PhD is in astronomy, but my background is in Earth and Planetary Sciences before that. You guys all probably know more about how to use a telescope than I do, because I'm a theorist. And so I model planets, and my research group really tries to understand the role that the geology of the planet plays in setting the habitability of that planet. And I really got into studying this when we first started finding a lot of exoplanets, right? One of the real main goals of the search for exoplanets is the search for life somewhere else in our galaxy, right? And as astronomers, we always focus on trying to understand where water is when we're talking about habitability. So I wanted to talk a little bit today about the many faceted role that water plays in planetary habitability, and why it is that we really focus on trying to understand and find water on rocky planets in particular. The number one reason is just water is really abundant. Water is made of hydrogen and oxygen. They're the number one and number three most abundant elements in the entire universe, right? And everything else is tiny in comparison. So there's this huge overabundance of hydrogen, and oxygen is the next most abundant element that can actually bond with it and make something interesting. This is the composition of the Earth in comparison to the universe. You can say oxygen makes up most of the mass of our planet, actually, followed by other elements, silicon and aluminum, and these are things that make up most of the rocks that make up most of the mass of our planet. Oxygen is the most abundant element in rocks, followed by silicon. Water is everywhere astronomically. I don't often get to show fancy astronomy pictures, but I figured I would show this one. So this is a galaxy far away, and it has a water maser. Maser is sort of like a laser, but in microwave. And this is sort of an excited state of water that triggers sort of a coherent emission. Water is everywhere in our solar system. I love this picture. This is an actual photograph. When I showed my husband this picture for the first time, he's not an astronomer or a scientist in any way. He thought I had sort of photoshopped a couple of objects on top of each other. But maybe you guys know what these objects might actually be. Anybody have guesses what system this is? Yes?
All those are obviously Saturn's rings, and in the back is its largest moon, Titan, and in front of it is Enceladus.
That's right, exactly right. We've got a photo from So this is the rings of Saturn. The rings of Saturn are super thin and amazing, and they're almost entirely surface, of course, is also covered in ice, water ice. And that big hulking moon in the back is Titan, very correctly identified. We have seen liquid on the surface of Titan. Unfortunately, it's not water, of course. This is from the Huygens probe that descended down through the atmosphere. The liquid that we see on the surface of Titan is methane. But we think deep in the interior, water actually makes up a significant portion of the crust of Titan. On Titan, it's cold enough that water, it basically acts as the rocks on the surface of Titan. And deep in the interior, there may be an ocean of water, although the jury is still out on whether that is the case or not. Water, we have found water on Mars many times. There's a joke. I didn't bother putting up any other photos here, but NASA now classifies Mars as a relict ocean world. We think that there's ample evidence that water was at play in the surface geology, and we do see it today in the regolith and in the polar regions as well. There's even water on Mercury, right? This is our innermost planet, the hottest planet in the solar system. There is water at the poles on Mercury in permanently shadowed craters at both the north and south poles. This was seen by the spacecraft Messenger, probably delivered there by the impactors that made the craters, and then the vapor sort of migrates into the cold regions and condenses and makes ice there. But that ice may have been stable for millions, maybe even billions of years on the surface of Mercury. But of course, Earth's surface water is really unique, right, compared to all of the other planets we've seen, all the other planets we know of. And even though it covers 70% of our surface, the oceans only make up 0.02% of the total mass of Earth, right? It's a really tiny fraction of the Earth, and it's really critical for our existence here. This is an infographic where they've taken all of the water on Earth and basically condensed it into this little globe. You can see it's smaller than the United States. It's very small. But this is actually less than half of all of Earth's water. And I'll tell you in a minute where the rest of it is. This is a slice through the interior of the Earth where we can see sort of the different layers going on in the interior. So we have the bulk of Earth is called the mantle. We live on the crust, which is so small as to be invisible on this diagram. But the mantle is mostly made out of rocks, very similar to our crust. Chemically, they're a little bit different, but in minor detail. And then we have a core made up of iron, nickel, metal. The inner core is solid, the outer core is a liquid, and it's the motion of the outer core that gives us our magnetic field. And so while we have one ocean mass, I'm going to call it an ocean mass of water at the surface, I'm lumping all of the water together as one at the surface. Within the mantle, we have at least one, possibly up to 7, some people may say even 10 times that amount of water locked up within the rocks of the deep interior. So what is that, the form of that water in the interior? Do we have like swimming pools or oceans of water in the mantle? No, so in the mantle, the water is stored in something we call nominally anhydrous minerals, NAMs. It rolls off the tongue. But most of the minerals in the Earth's upper mantle are magnesium silicates, so they have magnesium atoms, silicon atoms, oxygen atoms. But you can see there's no water, there's no hydrogen in the chemical formula of these minerals. The deep mantle is mostly made out of another magnesium silicate mineral called bridgemanite. That also doesn't have any hydrogen in its chemical formula. So water is stored in sort of like the spaces between the atoms that make up the chemical formula of these minerals. And it's stored in small enough quantities that it doesn't really affect the overall chemical formula of the minerals. You can sort of think of it as a sponge, maybe not that kind of sponge, but this kind of sponge, the rocks in the mantle. You can soak up a lot of water in a sponge, right, without changing the fundamental ornamental nature of the sponge itself, right? And that is what is happening with these rocks. The water is stored sort of in the spaces between the atoms in these different kinds of minerals. So this diagram over here on the left is showing us something that we call the water storage capacity, which is just how much water can you store inside of these minerals. So we're going from the crust of the earth down to the core, and the size of this green band is showing us how much water we can stick into these different kinds of minerals. And this water storage capacity is measured in high pressure experiments in people's labs, often using something called a diamond anvil cell. I have a colleague in my department that does this kind of experimentation, and this is an actual photograph of a diamond anvil cell. It looks really impressive here, but it's actually like this tiny. It's very small. But what we do is we use the diamonds because they're very hard. You apply pressure onto the diamonds, and you have you cut them so that they make a very very small, very narrow space, and you can put a small sample there, and you can compress it to huge pressures, comparable to the pressures we get down here at the base of the mantle. So using these kinds of experiments, people have measured the storage capacity, and we can see that we can stick a fair amount of water into different layers within the Earth's interior. So the amount of water we can stick into the upper mantle increases as we go to deeper and deeper layers. So this is 400 kilometers below the surface. There's this interesting region called the transition zone where the minerals go through different phases, and those phases have a much larger water storage capacity. But then in the very deep mantle, we think the mineral that exists, that occupies most of the space down there, has a very low water storage capacity. So there's a fair amount of water that can be in the mantle, and mostly in this sort of upper region of the mantle. But then again, because it occupies the majority of the space of the Earth, even a small concentration of water there amounts to a very large amount of mass of water. So our estimates for the number of oceans that exist in the mantle, different scientists sort of disagree on the absolute number, but the number sort of averages out to about the same amount of water in the mantle as there is on the surface. And this is based on experiments in a lab, but how do we know that there's actually water down in the mantle? Well, we know that by looking at samples of rocks that come out of the mantle. In particular, we have diamonds. Diamonds form in the deep mantle, and they contain what we call inclusions, little pieces of other minerals that also formed at those depths. The diamond is just made out of carbon itself, but it can trap minerals with different compositions. So this is sort of how a diamond forms at the ocean sort of sinks into the mantle, the ocean plate sinks into the mantle, and melting happens down here. And here we have some diamonds, and they get trapped in some volcanic flow that's trying to reach the surface, and they come up to the surface at sort of special volcanic locations. And what we have found in some of these diamonds is actually ice. Now the mantle is pretty hot actually compared to the surface. Temperature increases as you go deeper into the planet. Right, but what we found is not like the normal kind of ice that you see on the surface. This is a phase diagram of water showing the different phases that water can take. So this line here is showing the pressure. This is sort of normal atmospheric pressure. And this axis down here is showing temperature. So, you know, under normal surface conditions, we've seen solid ice, right? You have ice in your cup of soda or other liquid. We have liquid we know that there's water in the deep interior? Which is actually by measuring the composition of rocks that are coming out of volcanoes. By analyzing the composition of lavas, lavas come from the partial melting of material from the mantle. And so we can actually find water in these lavas as well. So there's many different kinds of volcanism that can happen. The Hawaiian islands, this is the island of Hawaii, and the Hawaiian chain are a kind of volcanic center called an ocean island. And it is sourced by a mantle plume that is coming from the really deep interior of the mantle, from down probably near the core mantle boundary. And what happens is that due to plate tectonics, the overriding plate is actually moving across this mantle plume, which is sort of stationary. And as the Pacific plate moves, the volcanic center, or the actual plume stays in place, but the plate is traveling across it. So we've created this series of islands, of volcanic island chains, through this process. But this relates back to the water in the mantle, because we can take a sample of this lava once it cools, and we can measure the abundance of water there. And it is consistent with these with this idea that there is about 1 ocean worth of water in the mantle, and specifically in the upper mantle where these kinds of lavas are coming from. The last thing I'll point out on this figure, though, is that you can see the size of the green bar is proportional to the potential water storage capacity of the different layers. And the biggest potential reservoir of water is actually the metallic core at the center of our planet. It turns out that hydrogen, which makes up most of water, dissolves really easily into metal alloys, and it may be abundant in Earth's core. This is another person's estimate of exactly how much hydrogen and water is stored in different layers, and you can see that the core makes up, this is an estimate of the different reservoirs that hydrogen is occupying in the Earth, and you can see that the core makes up, 3/4 of the total hydrogen on the Earth, which is pretty incredible, right? The core forms early in the Earth's history, and if that water had been delivered later, we might have actually had larger oceans if it couldn't have gotten into the core instead. So where did Earth get its water? Well, Earth got its water mostly during the process of planet formation. Planet formation is sort of a side effect of star formation. Stars form out of a cloud of dust and gas that sort of collapses down, and it ends up forming a disk around the star. And most of the mass of the disk ends up accreting onto the star itself, but some of the leftover material makes solid grains that can sort of gradually collide and hit each other and accumulate into larger solid objects like the Earth. Within the system, there is a lot of gas, right? The composition of this disk is basically the same composition as the star that gets made at the center. And so there's a lot of hydrogen gas and a lot of oxygen, and of course these readily combine to make water vapor in this planet-forming disk. And this is showing, this little diagram down here is sort of showing the regions where we might actually get water forming in these planetary disks where planets are forming. So Earth is down here at 1 astronomical unit, and Jupiter is here. And there's a temperature gradient in this disk that allows different materials to condense into solid form as you move away from the star. If you're too close to the star, then water can't condense into a solid at those temperatures because it's too hot. And we think in the protoplanetary disk that made the solar system, the water ice snow line was somewhere around the place where Jupiter actually formed. And what happened is that the formation of the giant planets actually mixed up a lot of the smaller things that were forming in the outer solar system, and kicked a lot of them inwards. what we're seeing is Jupiter and Saturn forming here. I'm going to show you a couple of time steps of a simulation of what happens to the small bodies. So these are all these little dots are asteroids, and they're color coded by the amount of water that they would have contained based on the location that they're forming in. So red is really low in water, and these blue objects out here have lots of water to them. So this is around 5,000 years into the simulation. And again, yes, we're moving to increasingly water-rich objects. And what we're looking for is the objects that end out over here in the terrestrial planet crossing region. So those objects can potentially then hit the planets like Earth and Venus and Mars. So this is now at 130,000 years into the simulation. You can see what we're seeing here is the semi-major axis and the eccentricity of the orbits of these small objects. They've all gotten really excited. And now a lot of them have started being scattered out at 350,000. And then this is at 1.5 million here. And you can see in this region out here that we said these objects could cross the orbits of the terrestrial planets. You can see we have a lot of these blue objects, a lot of these water-rich things. So we think that this is potentially one way that Earth got a good portion of its water was through delivery of objects from the outer solar system that basically got kicked inwards by the formation of the giant planets. An alternative view that's becoming popular nowadays, actually largely inspired by theoretical work on exoplanets, is that the water on Earth could have actually been created from reactions between hydrogen gas and oxidized iron oxide that's found within the rocks of the mantle during an early planetary magma ocean phase. So the reaction is down here where hydrogen gas would react with this FeO, which is found in rocks, and that would make water vapor and basically turn that iron oxide into metal, which could then sink down and form part of the Earth's core. If this happens early when the planet is largely is very hot from the process of formation, this process could potentially be very efficient. Okay, so a couple of potential sources for Earth's water, and it's something that scientists are still arguing about today, about exactly where Earth's water came from. I want to move now and talk a little bit about the astrobiology of this and how water has actually affected the evolution of Earth as a planet. And I'm going to talk about sort of three different things, the effect on life, tectonics, and climate. And we'll start with life. And life is the thing, I am not a biologist. So I can tell you the effect of water on life from an astronomer's perspective. So from our perspective, water is crucial for life. We know this. It makes up most of our mass as humans. We're mostly made out of water, and that is true for anything composed of cells. But water has lots of unique properties that really enable biochemistry. Water is a polar molecule and a universal solvent. So it's polar. It is not a charged molecule, but it has an uneven distribution of charge that allows it to dissolve lots of other things really readily. It is one of the best solvents in the universe. It is crucial for all of the biochemistry on Earth. It supports the structure of biology by creating cell structure, by allowing membrane formation through lipids. It also supports protein folding, which is really critical for all of the biofunctions, biochemical functions of your body. I'm going to stop here before I say anything terrible about biology, terribly wrong about biology. But this is largely why we are really focused on finding water on an exoplanet. The only form of life we know of, water is incredibly crucial for its development and its survival. And we don't know of any other compound that has all of the same critical properties as water does that would allow it to behave the same way. So I'm going to move on to things I know more about water, and I'm going to talk about tectonics. and how that's affected the evolution of our planet. You can just look around the surface at any geology and see water has had a really profound effect on the geology of our planet. This is, I believe, the falls, I forget the name of these falls, but these are in Arizona. And so these are floodwaters from some monsoon that has carved these crazy terraces and the canyon that's running downriver from these falls. But the overall water cycle, you may have learned in some sort of basic science class, is that we have water evaporating off the oceans. It makes clouds that precipitate onto land, that cause erosion, and that water runs back off into rivers. Eventually it makes its way back out to the ocean. And there is this nice cycle of water through the surface environment of our planet that really alters sort of the fundamental geology and structure of the surface. But this is actually, again, only part of the story. And what my group actually studies is the deeper water cycle. So the surface water cycle, it operates on relatively short time scales. Evaporation and precipitation is on timescales of hours to days. The deep water cycle that my group studies operates on much longer timescales, on the order of millions to billions of years. And this is looking at the exchange of water between the surface, where we have the ocean, and the deep interior, where we have all this water that has been trapped within the mantle, and these nominally anhydrous minerals. And there is a transfer of water between the deep interior and the surface through the process of plate tectonics. So on our planet, and really only on our planet that we know of, we have plate tectonics, where we have the creation of oceanic plate happening at centers called mid-ocean ridges through volcanism. So rock from the mantle comes up and melts and creates volcanoes along the mid-ocean ridges that creates new oceanic plate, and then the old cold oceanic plate subducts back down into the mantle. Subduction zones sort of rim almost the entire Pacific Ocean, and this is where we get a lot of additional volcanism happening in the area immediately above subduction zones. So places like Japan and the Philippines, where we have lots of explosive volcanism, those are just above subduction zones, where ocean plate is sinking back down into the mantle. And what happens is that the melt that is forming the oceans here in the mid-ocean ridge brings water to the surface out of the mantle, and this ocean crust actually puts more water back down into the mantle because water dissolves into the rock. We also get hydrated minerals forming in the ocean crust, and that brings water back down into the mantle. Now we can model how this affects the overall evolution. We can create a model that tracks the evolution of the water abundance in the mantle and on the surface over time by studying the process of the mantle basically shedding heat. But water actually modifies the properties of the mantle, and this is something that we also have to take into account. Water that is dissolved in these nominally anhydrous minerals actually lowers the melting point of those rocks so that they can melt at lower temperatures. So this is a diagram that is showing pressure and temperature here, and this blue line is the melting curve for a rock that doesn't contain any water. And then as we add water to that rock, then we progressively lower the melting temperature. And this purple line over here is the saturated melting curve, where we've stuck as much water into this rock as it can potentially hold. And you can see that at this deepest pressure, we have gone from a temperature of 1800 degrees down to a temperature of 1000 degrees, where melting is happening. This is a pretty profound effect on the behavior of the rocks of the mantle. This effect, the way that water is depressing the melting point of these rocks, it's basically the same reason we salt roads in the wintertime in places where it snows. The salt actually depresses the freezing point, melting and freezing, where the controlling basically the way that the rocks of the mantle flow or move over time. Viscosity really is something you're probably familiar with. It's like how fluid is something, right? Water has a very low viscosity. Oils have medium viscosity, and honey in our everyday experience has a pretty high viscosity. Think especially of cold honey, and like trying to get cold honey out of a jar. It takes forever, right? Because it has a very high viscosity. Rocks also have a viscosity because they flow and they move on million-year timescales. But the viscosity is also affected by the presence of water in these rocks. So this is showing the viscosity. The units here aren't super important. The red and the blue lines are for different kinds of rocks, and then when you add water to it, it goes down to these dashed lines. You can see the other thing that affects viscosity is the temperature. As we go to higher temperature, the viscosity of rocks drops down to much lower values. That's also true for honey, right? If you microwave honey, it flows much better. So in these units, I do have honey on here. The viscosity of honey is about 2 to 10 Pascal seconds. That's what this is here. So the viscosity of rock is about 10 to the 10 to 10 to the 16 times larger. So this is 10 with 16 zeros following it. So very, 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 very viscous in comparison to honey, right? But nonetheless, even though this viscosity is quite high, the rocks of the mantle do move, and what they do is they convect and they bring heat out to the surface, and that is also what allows the water that is trapped in those mantle rocks to come to the surface and become expelled to the surface. And so coming back to this diagram of this deep water cycle, what is happening is that the mantle is convecting over time. So heat that is coming off of the core drives material to become a higher temperature and becomes buoyant, and it rises, and then it gets to the surface, and it cools, and it wants to sink back down. And so there's this cycle of material coming from hotter material coming up and colder material sinking. And that material that is hot that is coming up, that is the material that can try to melt and bring water back to the surface. So the temperature of the mantle overall controls the rate at which this process happens, the rate at which this can happen. And hotter mantle moves more quickly and can bring water to the surface more quickly. Water lowers the mantle viscosity, which allows it to move faster and get rid of that heat faster, and so the temperature drops. So there's a bit of a feedback between the amount of water that is in the interior and the rate at which these processes can happen. And as the temperature drops, the mantle convection slows, but the convection would continue, the subduction would continue. We would continue to get material coming back down into the mantle, and that would allow the water to build back up, which would then create this feedback cycle. So one of the things we wanted to look at, because we're interested in how these processes operate not just on Earth, but on other planets that we may find that may have oceans and water as well, is how does this affect, how does this process change for bigger planets? One of the reasons we focused on larger planets is that many of the small exoplanets that we have found, we call super Earths. This is a diagram showing the number of planets we have found per star as a function of the planet's size. So Earth would be here, and you can see we haven't found many planets in that size range, but we found a lot of planets just a little bit bigger than that. And we have measurements of densities of some of these objects, and we think that the objects in this sort of peak of this planet histogram seem to be similar in composition to the Earth. And so we're hopeful that maybe the geology of those kinds of planets operates in a similar way to the Earth if they have similar compositions. So we built some models, and that model this process that happens for the Earth, where we're monitoring sort of the long-term abundance of water on the surface and the amount of water at the surface of a planet for planets of different mass from one side times the Earth, that would be us, up to 5 times the Earth's mass, shown by this cute little cartoon here. And this is showing sort of the surface area coverage of ocean that would happen as a result of just of this drawdown of water into the mantle. And what we can see is that the one Earth mass planet like us has a pretty stable ocean coverage for a very long time. This is out to 10 billion years. Whereas this big guy, the 5 ocean mass planet, it actually starts with no ocean. And it gradually builds up an ocean, and it eventually becomes a very large ocean in comparison to ours. So what we see here is that we have larger rocky planets could potentially have delayed ocean formation, and smaller planets, they do, I didn't include these on the slide, but smaller planets do gradually sort of lose their ocean back into the interior of the planet. Okay, the last thing I want to talk about is climate, and I'll try to get through this quickly so we have plenty of time for questions. Climate, so for astronomers, the climate that we're interested in is largely defined by the habitable zone for rocky planets. This diagram is showing in blue, this is the habitable region of a star, where we're showing how it evolves for stars of different masses. And it's moving over time here as a result of the evolution of the star's brightness as it changes over time. What you can see is that the Earth basically stays in the habitable zone of its star for the entirety of this simulation. This down here is Proxima Centauri b, which is our closest neighbor, and it is a planet we believe is in the present-day habitable zone of its star. You can see early in its lifetime, it was interior to that habitable zone. And the habitable zone, we think, is defined as the orbital region where we believe that liquid water would be stable on the surface of these planets. And it's defined really by climate models for these planets. The climate, we believe, of rocky planets is determined largely by something I'll talk about in a moment. It's the carbonate-silicate cycle, which on Earth at least helps maintain a very habitable climate temperature over long timescales. And the inner edge of that habitable zone is really set by the greenhouse effect, and is largely dominated by water vapor in the atmosphere. So I'll come back to that in a moment. The carbonate-silicate cycle is a process driven by weathering on the surface of the Earth. And it is really only allowed by the fact that we have water in an ocean. So what happens is rain falls down onto rocks. There is carbon dioxide dissolved in that rain and other things that make it a little bit acidic. And as it falls onto rocks, it actually pulls some elements out of those rocks and washes them down into the oceans. In particular, it pulls calcium out of different minerals, and that calcium reacts with carbonic acid in the oceans, and it makes calcium carbonate. And we get a little bit of CO2 out of that as well. So what happens is we have this cycle where we have CO2 in the atmosphere, it dissolves into water, it reacts with different elements in the water, and it eventually precipitates out. And so what happens is most of the carbon dioxide on the Earth is actually locked into rocks called limestones. Seashells are all made out of calcium carbonate. These are organisms, sea organisms, have figured out how to pull that calcium carbonate out of the ocean as well. But when that sinks down to the bottom of the ocean, it makes a rock called a limestone. Limestone, if it becomes a metamorphic rock, turns into marble. And so what happens in this feedback cycle is we have carbon dioxide in the atmosphere. If we have some perturbation to a warmer climate, what happens is that increases precipitation, which creates increased chemical weathering, and then CO2 is drawn more strongly out of the atmosphere by weathering, and it gets trapped into rocks, and then it reduces back to sort of the original temperature. So the carbonate silicate cycle is sort of a thermostat It is a negative feedback cycle, and it sort of helps maintain a climate temperature on the Earth. If you look at Venus, Venus's atmosphere is mostly CO2, and it definitely is not a climate habitat temperature on the surface. And the CO2 hasn't been drowned out of its atmosphere, largely because it doesn't have water on its surface to help mediate this reaction. So Earth and Venus have similar amounts of carbon dioxide, but Venus's is all in the atmosphere, and Earth's is mostly trapped in rocks. So this is something that we're looking for rocky planets as well. Is our hope is that many of them will have water at the surface, so that their climates can be regulated in this way. The other effect I wanted to mention from water is the greenhouse effect that sets the inner edge of the habitable zone. And it is mostly driven by the fact that water vapor is actually a really strong greenhouse gas, right? So a greenhouse effect, you probably are all familiar with this, but we have sunlight that comes in. Some of it gets reflected off of the atmosphere, mostly by clouds. But what doesn't get reflected mostly makes it down to the surface, where it's absorbed by the surface, and the surface then re-radiates it back at infrared wavelengths, and the atmosphere traps it when we have the right kinds of gases in the atmosphere. This is showing the wavelength regions where different kinds of gases will absorb infrared radiation. So this is infrared wavelengths. The two different gases shown here are water vapor and carbon dioxide. Now, through just popular media, you probably all know that carbon dioxide is a pretty strong greenhouse gas, largely because it absorbs a lot of infrared radiation that the Earth itself is emitting into the atmosphere, and it traps that radiation between the atmosphere and the surface, rather than allowing it to escape out into space. You can see water vapor occupies a much larger proportion of this plot, right? Water vapor is actually a much stronger greenhouse gas than CO2 is. The reason it is much less of a problem for global warming is that it condenses, right? It goes up into the air, it condenses into a cloud, and then it comes back out. So it's very transient in our atmosphere. But the effect of CO2 on climate change also does actually factor in the effect on water vapor. That is something that climate models do include. So the effect water vapor has on the greenhouse is that if you have a small temperature increase at the surface, you will potentially caused by additional CO2 in the atmosphere, you get a stronger greenhouse gas, which increases the surface temperature, and that causes more water vapor to evaporate, right? But we have higher humidity when the temperature at the surface is higher. So that increases the water vapor concentration, but water vapor is a greenhouse gas, so that causes the temperature to go up, right? And so there's this positive feedback loop now where this will just continue to increase. As you increase temperature, you get more evaporation. And what happens on the inner edge of the habitable zone is that this runs away entirely. And the entire ocean would evaporate, and you would actually get so hot if our entire ocean evaporated that you would melt the planet. These planets, like Proxima Centauri b, are interior to their habitable zone. That means they're in this runaway greenhouse phase for the initial period of their lifetime. And if they had an ocean like the Earth's, they would have been totally evaporated, totally in the atmosphere, and might have actually melted the surface. So one of the questions we ask about these kinds of planets is are they actually, in fact, habitable? Do they still have water? One of the issues we think might happen, this is a cartoon of a model where we have a rocky planet here, we have a metal core, we have a mantle that is mostly melted at this point because we have a lot of energy from our star, and we're in the runaway greenhouse phase. So we have water vapor in the atmosphere. And the small stars like Proxima Centauri actually put out a lot of damaging radiation, X-rays and ultraviolet rays, that we think can drive a lot of atmospheric escape. So one thing that we are worried about with these kinds of planets is that they go through this runaway greenhouse phase, they have water, but that water vapor is in the atmosphere, and this early radiation from their stars actually drives that atmosphere to escape. So that when the habitable zone moves inward, and they are in the habitable zone, maybe they've already lost all of their water. So, so this is something that we have looked at through models. And what might happen actually is that we might only lose the hydrogen from the water and leave behind an atmosphere that's mostly made out of oxygen. This would be interesting, right? Because on Earth, oxygen is produced only by biology. It's considered a biosignature. And so it's possible that these planets not only don't have any water left, but they have oxygen in their atmospheres. That's a false biosignature. We looked at this pretty extensively, and we found that there are different kinds of planets that are more likely to build up this abiotic oxygen that is a false biosignature. And it depends on the initial abundance of water, and it also depends on the composition of their rocks, how much iron oxide is present in their rocks. In this diagram, those planets that had the most water were more likely to build up oxygen. But this was very sensitive to how close the planet was to the star and how large the planet was. So this is a diagram showing for a 1 Earth mass planet versus a 10 Earth mass planet. And yellow here is much larger oxygen atmosphere. So the larger the planet and the further away from its star, the less likely it is to build up this false positive. So what we suggest from this is if we're looking for life on another planet, we want to look at planets around slightly larger stars that don't go through this process. And we want to look at larger planets that are a little bit further out in their habitable zones so that they are less likely to have built up these false positives. So here's my summary. I'm going to end there, but I'll just say water has really fundamentally shaped the climate and the tectonics of Earth. It has made life possible on our Earth, and hopefully we will find another planet like it someday. So I'll stop there. Yeah, I'm very happy to take questions. Here, okay, I see your hand first.
What is the molecular formula of a diamond, and what are the stages that it goes to producing a diamond, the molecular formula stages?
So a diamond is pure carbon. It doesn't have a molecule, it is just carbon. C. It is C. So what happens is usually we have basically in the subducting ocean plate, we'll have carbon in the form of carbonates. So it'll make these calcium carbonate rocks like limestone. And as you bring that rock further deeper into the mantle, it melts. And through some reactions with other rocks, you sort of strip the oxygen off of that carbonate, and then you can make the diamond. So the diamond is only made in the deeper mantle. It has to reach a certain critical pressure in order to make a diamond. If you did this process in the upper mantle, you would make graphite instead.
It's condensed carbon.
It is condensed carbon, yeah.
Okay.
Yeah. Other questions? Yes.
Did Mars used to have water in the atmosphere like the Earth?
Yes, water. Mars probably had potentially it had some transient liquid water at the surface. Anytime you have a liquid on the surface, you're going to have water in the atmosphere, and it does still actually have water vapor in its atmosphere today. And the Mars MAVEN mission has observed that water actually still continuously escaping.
So how come Mars doesn't have the water that it used to have that the Earth does?
Most of the water on Mars has unfortunately escaped. So what might have happened is that the hydrogen and oxygen might have separated from each other at some point in the atmosphere. We know that the surface of Mars has been highly oxidized, so that oxygen might still have stuck around and gone into reacting with different minerals. But Mars is so much smaller than Earth that it's hard for it to hold on to hydrogen. So Earth is also always losing hydrogen, but only a little bit at a time, whereas Mars is so small that the hydrogen escaped really rapidly.
Does Mars have a magnetic field like the Earth does?
Mars used to have a magnetic field, potentially for maybe 500 million years, but it does not have a magnetic field anymore.
So
Yeah.
does that mean it'd be a waste of time to try to terraform it?
I know some really smart people people who are working on trying to terraform Mars, so I won't say that it would be a waste. I think it's a very, very, very long prospect in order for us to actually be able to achieve that process. I think you're talking like hundreds of years in order to make that possible. And so, I mean, I think it would be cool just to study Mars as it is personally, without trying to change it, because I'm curious about its history. Sorry, did I see a question back here? No, okay. If not, down here in the front again. Yeah.
Is Mars habitable now? Because I think a long time ago, I was in research, and even 100 years ago, I built space capsules that went to planets that circles the Earth, and we went to the moons, and I went to Mars before too. I was wondering, is Mars habitable, and also the planets around Earth, are they habitable? I explored it before. It was habitable.
Mars is probably not habitable right now. It is potentially, with a lot of technology, you could establish a small region where people could survive there, but only if you brought in a lot of resources from the Earth continuously, I think, right now. I think certainly right now we couldn't survive on the surface by itself. The atmospheric pressure is far too low for us. We definitely need some kind of pressurized environment to survive. The atmospheric pressure on Mars is only 1,000th of our atmospheric pressure. And so that's far less than even the highest Mount Everest, right? It's hard for people to survive on Mount Everest, and Mars is far worse in terms of atmospheric pressure. It also doesn't have any liquid water on its surface right now, so we would have to basically try to pull water out of the atmosphere for the people that were on the surface. And then other things, like it doesn't have a magnetic field, so there's a lot more radiation that reaches the surface, so that's that's another big risk. Yeah, so right now, unfortunately, not without a lot of assistance.
I remember when I went there, we put trees there, and it felt normal, like just like Earth.
That would
I
be
think it's
amazing.
habitable.
Yeah.
I was wondering about the nitrogen in Earth's atmosphere.
Sure, yeah. Yes, yeah, we have lots of nitrogen in our atmosphere.
Nitrogen.
Sorry?
N.
Yes,
Nitrogen.
nitrogen. Yeah, nitrogen. Yeah, so nitrogen also probably reached the Earth through the same mechanism that water did. Probably from those asteroids that were scattered from beyond Jupiter and came to the Earth. And so we think nitrogen reacts much less with rocks than water or carbon dioxide does. And so there is not nearly as much sequestered into the mantle as there is water or carbon. And so we think largely once it entered the atmosphere, it's kind of been relatively stable over most of the Earth's lifetime. And so over most of the Earth's lifetime, we've probably had roughly this, within a factor of 2, the same amount of nitrogen as we do today.
Okay, thank you.
Yeah. Yeah, question back here.
Looking into the future of our planet, what's going to happen to the water?
Oh, what's going to happen in the water? Yeah, great question. So at some point, so this process of plate tectonics is gradually going to pull some of the water down into the mantle. It's probably not going to pull all of it, because what's going to happen is plate tectonics at some point is going to shut off, just because there will no longer be enough energy, internal energy, to drive basically the melting that creates the new plates. And then if that happens, then there's no force also pulling the plates down. So it's probably not going to pull all of the water down into the mantle. What will also continue happening is that the sun is getting brighter, right? It's going to continue getting brighter for the next 5 billion years until it leaves the main sequence. And then it's going to start to expand, right? And so at some point, within the next 5 billion years, it is possible that we may end up in a runaway greenhouse phase at some point. I'm not sure if that's going to happen before or after the sun swallows the Earth or not, though. Yeah, question back there.
In your research, what have you found most interesting or shocking?
What have I found most interesting or shocking? So I didn't talk much about new exoplanet science here, but one of the things that we have been discovering with the James Webb Space Telescope is that indeed most of the small rocky planets that we have been able to observe, which are all pretty hot, so they're all hotter than Venus. So far, only the ones that are the absolute hottest actually have atmospheres. And that is pretty counterintuitive, right? So the colder of the rocky planets that we have managed to study so far don't seem to have atmospheres at all. Maybe they have an atmosphere, maybe the size of Mars, but definitely nothing the size of Earth's atmosphere or Venus's atmosphere. But the very hottest planets we have seen that appear to be in sort of what we call a permanent lava world state, where their surfaces are so hot that they're always liquid rock. Those ones, we see atmospheres, and that is really puzzling. So that's my favorite discovery of the past 5 years. Yes.
What are they composed of, the atmospheres?
What's that?
What are the atmospheres?
What are the atmospheres composed of? That's a great question. We don't actually know yet. So some of them may have a lot of water vapor. Some of them may be very carbon dioxide or carbon monoxide rich. But one of the ways we've been able to discover this is through the technique called secondary eclipse, where we can essentially just measure the temperature on the day side of the planet. And we can compare that to the temperature on the night side of the planet, which we also get through a transit. When we see a big contrast there, we think that the planet doesn't have an atmosphere, because the atmosphere is actually really good at moving heat from the day side around to the night side. And what we found is that there are some planets where we don't see a big contrast. And so that's the evidence that we have for atmospheres on these hot planets. So far, we have not actually been able to directly characterize the chemistry of those atmospheres yet, but that is something that we're actively working on.
Not enough light to use spectrum.
The problem is that the spectra are pretty noisy, so we just need to get more observations to improve that. Yeah.
This is off topic.
Sure.
You mentioned that the source of the Earth's magnetic field. I thought you said it was the mantle, but I could have missed.
So it's the metallic core.
Okay,
Yeah, so it's the metallic core. So the Earth has both a liquid outer core and a solid inner core. And so it is actually convection that is happening within the outer core that drives the magnetic dynamo. So what is happening is it's a conductive fluid that's in constant sort of turbulent motion. And we are basically, so it's a moving conductor that is moving through the sun's magnetic field, right? So it generates a dynamo. I'm not a dynamo person, so
Right.
you'll forgive me. That's about the best I can explain.
Got it. Thank you.
Yeah, question back here.
How does a saturated rock have lower melting point? It should be higher, but water in there as well.
Yeah. So what happens is, so it's basically the same thing. Yeah, as salt and ice, right? The more salt you add to ice, the lower the freezing point gets, right? So the temperature at which you go from solid to liquid. So melting point is, same thing, right? Going from liquid to solid. So it's the same process. But what happens is essentially it sort of disrupts some of the chemical bonds in the rock, and it allows it to melt at a lower temperature. If that makes sense. Yeah, question over here.
So the process that would decrease the tectonic activity would also then decrease the magnetic field?
Yes. Yeah. Essentially, all of the motions that are happening inside of the Earth are driven by the inside of the Earth is basically trying to get rid of heat. So the planet has a lot of energy that is mostly left over from planet formation. Planet formation is a highly energetic process. Things are colliding together. You get a lot of gravitational energy, and so almost all tectonics on the Earth is driven by that residual heat trying to come out. So the planet is gradually cooling off over the billions of years of its lifetime. It started off much hotter than it is today, including the core. As the planet's interior cools off over time, all of those motions are going to get slower and more sluggish. Yeah.
Does the moon help slow down that dissipation of heat?
Does the moon? So the moon, no, in theory, it is possible that the moon could actually help increase that through tidal forces.
Friction would cost you.
So, unfortunately, there's a moon of Jupiter that is the most volcanic moon in the solar system, Io, right? And that is actually driven largely by tidal forces. So between Io and Jupiter and the other two moons, Europa and Ganymede, that it's in an orbital resonance with. And so our moon is tidally locked to us. And so there's been a lot of tidal, basically tides sort of dissipate orbital energy, and that dissipation takes different forms. On Io, because Io doesn't have an ocean of water, the tidal dissipation is basically stretching and straining the rocks itself, and it creates a lot of heat, and it melts the rocks and causes a lot of volcanism. Now on Earth, actually most tidal dissipation happens through our ocean tides. It's actually just friction between the water and the continents that dissipates most of that energy. If we didn't have our oceans, we would probably actually have a lot more volcanism because of that process.
Let's take about 2 more questions.
Sure. Is there a question here?
Yeah, what is preventing the crust from moving more into the mantle?
Most of it is just buoyancy. So the continents especially are a lighter, lower density rock than what makes up most of the mantle. So the oceans subduct because they actually, as they get older and colder, they do actually start to become denser than the rocks that are underneath of them. And so eventually they do sink down into the mantle. But the ocean crust is constantly being regenerated at these mid-ocean ridges. This was, so there's a process of magnetic reversal that happens. Sometimes our Earth's dynamo, like right now the North Pole is pointed at the north, and sometimes it switches. And this process happens on relatively regular timescales. And one of the ways that we discovered that the theory of plate tectonics was accurate was in sort of World War II, when submarines went out and started mapping the ocean bottom. They discovered that there are these stripes of different magnetic field direction that are recorded in the rocks on the sea floor. And what happens is that rock is being constantly regenerated at the mid-ocean ridges, and it records the direction of the magnetic field at the time it was created. And so we can see that the ocean floor itself, the oldest ocean floor, is only about 200 million years old, whereas the oldest continent is about 3.5 billion years old. So continents, they're lower density rock, so they just stay at the surface when they're created. But those oceans, they get constantly regenerated. Yeah. Yeah, question, Ray.
Are there beneficial effects of tidal pull between the moon and the Earth as pertains to sea life in the ocean, like they mix the sea life?
I mean, certainly sea life has definitely adapted to the fact that we do have tides, right? And certainly I think there are forms of sea life that do benefit from it, like the stuff that lives on the shore really sort of relies on that cyclical nature of wet and dry cycles. If you talk to people who work on origins of life, they also think that tide pools are an interesting place, and this wet and dry cycle might have been a key process that could have helped drive some of the early biochemistry that was necessary for the first cells to form. So yeah, maybe, potentially.
Well, with that, if you do have more questions, I certainly welcome you to come and stay. But thank you so much for coming out.